All right. Let's look at this. Let's look at this problem here. Okay, so this is, I'm just copying these straight out of the textbook here. All right. So this one says researchers conducted a randomized, double-blind clinical trial in which some patients with schizophrenia were given the drug clozapine, I'm not sure, and others were given haloperidol. And after 1 year, 61 of 163 patients in the clozapine group showed clinically important improvement in symptoms compared with 51 out of 159 in the haloperidol group. Identify the type of statistical method that is appropriate for the data but do not actually conduct the analysis. Okay, so that's kind of the question you might get in that one section. And then later on in the test, you might see a problem with this kind of setup, and I will just tell you, do this kind of test, right? Because it's hard to ask which test should you do and then have like follow-up questions that don't give away the answer. So you have one section that just asks which test should you do, no follow-up questions, and then later on I'll just say do this test, and there's a bunch of related things. Okay, so what is our answer here? Okay, well let's look through this. All right, what is our response variable, and what type of data is it? Okay, so what we're looking to see. Okay, so what are we hoping to identify, or what are we hoping to find in our study here? If the medication is helpful, right? Like which medication is better, right? And how did we decide if something was better or not? What did we want to see? Yeah, improvement in symptoms. Okay, improvement in symptoms, is that a numeric or categorical variable?
It could be either one. Like your response variable could be number of schizophrenic episodes.
Okay, sure. Okay, as it's presented here, is the data numeric or categorical? It's categorical, right? The response variable is categorical. And all we have is they showed improvement or not. Showed clinical improvement, okay? And however that's defined, we don't know the details, okay? That's beyond the scope of our course. Showed clinical improvement. All right, so you might have like the DSM-5 or something, and they have kind of these like a list of things that you check off, and if you check off like 6 of them, you're like this thing, and if you only check off 4, then that means you've improved or something. I don't know, okay? So it's categorical, showed improvement or not, okay? And then what's the predictor? Type of drug, also categorical, okay? All right, so we've got a response variable that's categorical, a predictor variable that's categorical. So what is the appropriate statistical method here?
Chi-squared independence.
Chi-squared test for independence. Okay, and we're looking for, is there a relationship between the two variables? All right. Okay, so 13.2.2 will be conduct an analysis. Okay, So if we're going to do a chi-square test for independence, let's go ahead and do this. All right. All right. So earlier we did the symbolic representation of the hypotheses. What would our hypotheses be in words?
The probability of improvement given some drug.
Okay, I feel like we're still talking symbolically here. So what we want to say, just kind of in words, is that drug type does not influence or is not linked or associated with improvement in symptoms. Right? So that would be that they're independent. Drug type is not associated with improvement in symptoms, or drug type and symptoms are independent. Okay, and then the alternative would be that they are associated. That would be the non-directional alternative. Can we have a directional alternative for this thing? We can, okay? Most chi-square, I don't know about most, but a lot of chi-square tests that are non-directional. But when you only have 1 degree of freedom, and we only have 1 degree of freedom here, we can have a directional one, right? So possible, so non-directional would just be drug type is associated with improvement. And then a directional one, what would a directional alternative look like? Yeah, so we would say clozapine patients, maybe yeah, I don't know, clozapine is more effective than haloperidol, or vice versa or something. All right. Okay, how would we go about conducting the test? So let's set up our observed data. What is our observed data? I would set up a 2x2 table. Okay, and I'm going to say we have those who improved and no improvement. And then we've got clozapine, haloperidol. Okay, and so we have 163 total in the clozapine group, 61 here, and 102, which means we got a 102 here. Over here I have 159, 51 here, 108 over here. So, so this row total is 112, this row total is 210, for a grand total of 322. What would be my expected counts? Yeah, we would do row total times column total divided by grand total, right? Something like that. And really, we only need to find one of the cells, right? So I copy kind of the row totals and column totals. Okay. And we really only need to find one cell. If I find one cell, let me just write improvement, no improvement. Okay, and then so for, just do kind of row total times column total divided by grand total. All right, so if I do 112 times 163 divided by 322, 112 times 163 divided by 322, I get 56.695, 56.7. Okay, and then we can fill in the other squares. All right, and then you go and you do the rest of your chi-square test. I think for time we got started, you can do the rest, right? Look it up in the t-table, or chi-square table, 1 degree of freedom, number of rows minus 1, number of columns minus 1. And you have you had a problem like this in your quiz. Okay, is that good? All right, let's look at the next problem in our textbook here. All right, it says a biologist collected data on the height in inches and peak expiratory flow, PEF, a measure for how much air a person can expire for 10 women. And here are the data. And is peak expiratory flow, PEF, related to height? Okay. What's the appropriate test here? Okay, so what kind of variables do we have? Yeah, we have 2 numeric variables. So that means we are going to do correlation, right? Correlation. Okay. Shall we do some correlation? And correlation. Let's keep this easy. Let's just like on the exam, I'll be nice. I don't know if this is nice, but if I ask you to find correlation, it'll only be for like 5 data points, 4 or 5 data points. It's just because it gets really tedious when it gets much bigger than that, right? So let's just go ahead and we'll find correlation for these 5 data points here. Okay, so I will call height X, peak expiratory flow Y, and then I'm going to kind of just set up columns for myself. X minus X bar, Y minus Y bar, and then we're going to have X minus X bar times Y minus Y bar. All right. Okay. All right, so the mean of X, whoops. So X bar is 64.2. Y bar, it's just the mean of these 5 numbers, is 430. and the standard deviation of x, which you can do is 1.3038, and the standard deviation y is 62.0484. Okay, so what we'll do is we're going to do x minus x bar. So we're going to get 63 minus 64.2 is negative 1.2. Negative 1.2. I have to get these to line up. 1.8. 65 minus 0.8, and 64 minus this is negative 0.2. Okay. 430. Okay, so 410 minus 430 is negative 20. Here I get positive 10. 450 minus 30 is 20, positive 20. 510 and minus is 80, and 340 minus 430 is negative 90. Sorry, thank you. Okay, and now we multiply. Okay, I'm not this good. Well, maybe I can do it. Okay, negative 1.2, that's 24, positive 24. This will be negative 12. 220 times 1. Okay, this actually isn't so bad. 36. 0.8 times 80 is 64. And negative 0.2 times negative is 18. Oh, okay. That was nice. All right. And then what do we do now? So kind of our formula for R is 1 over n minus 1 over the standard deviation of x, 1 over the standard deviation of y, times the sum of x minus x bar times y minus y bar. It's really 1 over n minus 1 times kind of z of x and z of y, but we can kind of pull out the standard deviation of x and standard deviation of y. Okay, so the sum of all of this, 24 minus 12 is 12. 36 and 64 is 100. 100 plus 12 plus 118 is 130. Okay, and we have n equal to 5. So I'll plug this in. R is going to be 1 divided by n minus 1 is 4. Standard deviation of x, 1.3038. Standard deviation of y, 62.0484 times the product of sum of the product is 130. Okay. So we'll go ahead and plug all of this in. Okay, so I'm going to do 130 divided by 4 divided by 1.3038 divided by 62.0484. Okay, I get a correlation R of 0.402. Okay, so that's correlation. All right, let's do a test for significance. So the null hypothesis will be rho is equal to 0 or no correlation exists in the population. And then the alternative, maybe we'll say rho is greater than 0, right? We'll say we expect taller people to have bigger lungs. I think that's a reasonable alternative or something, right? We expect there to be positive correlation between We'll say there is positive correlation. Okay, so the test statistic is r times the square root of n minus 2 divided by 1 minus r squared. So I plug in 0.402 times the square root of 5 minus 2 divided by 1 minus 0.402 squared. All right, I need a better calculator. Where's my good calculator? Okay, so 0.402 times the square root of 3 divided by 1 minus 0.402 squared. Okay, and I get 0.76. Okay, and we have degrees of freedom equal to n minus 2. We have 3 degrees of freedom. So we're going to look up 0.76 in our t-table with 3 degrees of freedom. Where is my reference tables here? All right. Okay. 3 degrees of freedom. Okay. And the first number here is 0.978. And we're smaller than that. So our tail area is greater than 20%. Okay. So our p-value is greater than 20%. Do not reject the null hypothesis. And we'll say we do not have evidence that PEF is associated with height. Sorry, I'm squeezing this all in here. Okay, and that's probably a consequence of having only 5 data points, right? If we looked at all 10, maybe there's a relationship. And if we looked at more people, I'm pretty sure there's going to be a relationship between height and basically lung capacity here, how much air you can breathe out in a minute. I wonder how they measure that. Like, are they hyperventilating when they do this, or how are they?
Oh, I've had that done. They hook you up to something.
They hook you up, and then you just
I
blow
remember blowing into a mask.
Blow really hard into the mask. But how do you not hyperventilate and pass out or something? I don't know. You just and I don't know.
Just like once.
Oh, you just do it once. Oh, okay. All right. Very good. Okay. I imagine it would be related to height. Just a lot of things kind of go together with height there. Okay. But with 5 data points, we don't have evidence yet. If I asked you to find the best fitting line, can you guys do that? Right, so you have equations for slope and intercept somewhere in your chapter 12 notes and chapter 12 textbook. I think maybe I'll just keep going. Is that all right? Okay, so we'll do that for the next problem. Okay, so, be prepared to find the slope and intercept there. All right, let's look at this one. I guess you can, on your own time. Maria is 1 inch taller than Annika. How much greater would you predict Maria's PEF to be than Annika's? How would you even answer that? What would the answer be equal to? Maybe I'll throw this in the notes. Okay, so we haven't done the calculation, but what would we calculate to answer this question?
Do the equation and have like 1 unit higher.
Yeah, so what would that be equal to? It would be equal to the slope, right? So the slope tells you how much your prediction changes every time x goes up by 1. Okay, so this answer is equal to the slope, which would be r times sy divided by s sub x. Okay, and because the interpretation of the slope is
the change in y with a 1 unit increase of x.
The change in our prediction. Yeah. So and it's not really that. So we treat our data as fixed. So it's not that we're actually taking it's not like we can take someone and just stretch them out 1 inch. You can't just add 1 inch. But it's the idea that if you have one person with this thing and you have another person whose measurement is 1 unit higher, in this case Maria is 1 inch taller than Annika, then Maria's prediction, our prediction for Maria, would be whatever size the slope is more than Annika's. Okay, interpretation of the slope is how much we expect y to change if the x value is 1 unit larger, or 1 unit greater. All right, let's go to the next one. (13.25) Geneticist self-pollinated pink-flowered snapdragon plants. I think this is the example I'm always using for this type of problem. So, and we want to know if they're, we end up with 22 red plants, 52 pink ones, and 23 white plants. And we want to know if this fits the genetic model, which says we should get 25% red, 50% pink, and 25% white. So what's the appropriate test here? The chi-square goodness of fit, right? Okay. I'm not going to bother working through it. Oops. All right. We did not cover the section needed to do 13.27, so we're not going to do 13.27. But let's look at 13.28, and I'll just kind of here. Oops. That's not here. All right, so 13 to 8. How do I do this? I guess I'll. So 13 to 8. The data look like this. All right, so here we want to look at the distribution of trees in an area, and they're trying to count how many trees are in a 100 square foot thing, but they're like, does it matter if we section them off in squares, or should we pick circles, or should we look at rectangles? Like, is this going to affect how many trees end up in the thing, or maybe it doesn't matter? So they want to know, does the shape of the plot that they use, does that affect the tree count? So they did some square shapes, they did some round shapes with rectangular shapes. Okay. What kind of analysis would we use here? ANOVA, right? One-way ANOVA. All right. Okay. And the null hypothesis is basically that the mu for the square is equal for mu for round, which is equal to mu rectangle. That the means of all kind of three populations are the same. The alternative is that at least one of these things is different. So does that make a difference? All right. Okay, this one, all right. Okay, 13 to 10. So there's some of the problem, and here's the rest of the data. Okay, so let's take a look here. It says a sample of 15 patients were randomly split into two groups as part of a double-blind experiment. The 7 patients in the first group were given Demerol and reported the following number of hours of pain relief. And then the 8 patients in the other group were given an experimental drug and reported the following numbers of hours of pain relief. So how might these data be analyzed? So we've got 2 groups, numeric response. Okay. So what do you guys think? Okay, so yeah, so we have independent samples, and so so we have 2 samples and they're independent. Okay, and so actually, I would say, you know, maybe you have a couple options here. We might say the t-test, okay? We can do t-test or confidence interval for mu1 minus mu2. But I would say maybe if we look closely at these numbers, we might want to do a Wilcoxon-Mann-Whitney test, okay? So if we look at this data set, right? So you remember how we can detect outliers? Okay, so I'm going to arrange these from least to greatest. So I've got 0, 1, 1, 2, 2, 3, 4, and 8, right? And we got 8 patients, 1, 2, 3, 4, 5, 6, 7, 8, okay? So I'm going to do a dotted line right here. This is our median. And then a dotted line right here, this is Q1. And a dotted line right here, this is Q3. Okay, so Q1 is equal to 1. Q3 would be equal to 3.5. And so my IQR is Q3, 3.5 minus Q1. I have an IQR of 2.5, okay? And so my upper fence is Q3 plus 1.5 times the IQR. And this is like a throwback to week 1, was it? Okay. Okay, so we're gonna do 3.5 plus 1.5 times 2.5, which 3.5 plus 1.5 times 2.5, and that is 7.25. 7.25. So technically 8 is an outlier. Okay, so if you have an outlier in your sample and you have a small sample, so the outlier is kind of an indication that your data is not normal, and then the fact that we have a small sample indicates that we probably should not use the central limit theorem. Okay, so we have an outlier. Which kind of the data, which means the data is not normal, is, I'll say, unlikely to be normal. And we have a small sample. Okay, so we cannot assume CLT applies, and that means we should use
Would you like for us to calculate that later?
what's that?
On the exam, if we get a similar problem and we decide to use the Wilcox,
Yeah.
you want us to show that.
Well, it's multiple choice. Okay.
Oh.
So
That's right.
yeah. So
The options wouldn't put us in a position where we have to select the best.
How do I tell you what I'm gonna ask of you without telling you what is the problem that I wrote on the exam? Okay, so one section is identifying which test to use, right?
Mm-hmm.
And so you may or may not have to do something like this to decide which test to use, right? And I would say in this case, the answer you should pick would be the Wilcoxon-Mann-Whitney test. Okay. In a separate part of the exam, I will tell you, here's some data, use the Wilcoxon-Mann-Whitney test. Or here's some data and use the t-test for 2 independent samples. Okay? And so if you chose incorrectly which test to use here, that's one problem that you get wrong, and not like you chose wrong and so everything else that follows is wrong, right?
Okay.
So So there's one part of the test is which test do you use, and you either get those right or wrong. And then later on, I'll have some kind of scenario, and I'll say, in this thing, use this test. Okay. Yeah.
I don't remember this test, but if we do Wilcoxon, we could have also looked at the first series of numbers rather than the second.
Well, yeah. So for the Wilcoxon, Mann-Whitney, yeah, you should look at both. Like if you have a small data set, you should just say like, does anything look like an outlier here, right? And so you kind of look and you go, is 13 an outlier, or is 2 an outlier? Is 8 an outlier, or is 0 an outlier? It's a little bit of a, I guess, like which one do we do first? It's a little bit of a gut thing, and then you kind of just check, all right? Or the other thing is just, is it reasonable to think that this thing is normally distributed? Okay. And anytime we're talking about time, in general, it's not going to be normal. Especially when the minimum is going to be 0 or something. So anytime you talk about like the time for something, like how long does it take to run a marathon? Okay. It's not going to be normal. It's going to be like, they just broke the world record on something, right? Like, how fast did the guy run the marathon? I don't remember. Really, really fast. So there's kind of a lower bound. No one's going to go faster than this world record thing, okay? Or it's very rare. And then, a lot of people will finish, I don't know, 4 hours-ish. I don't know how long a marathon takes, okay? And then some people will take like, I don't know, 10 hours or something really long, right? Like, yeah. So anyway, so you're going to get this very, so generally time-based things are going to be very much right skewed if there's not like an upper limit for something, or left skewed depending on which one's kind of like the cutoff, right? Like you have up to 30 days to submit something, it's going to be left skewed. You're going to have a whole bunch of people probably taking the maximum amount of time to complete whatever assignment was given to them, and then it'll be left skewed in terms of like some people like to turn things in early, and then or other stuff. But anyway, not too worried. And again, central limit theorem says if you got a big sample size, and we don't have a strict rule, but roughly if it's 25 or more, you can assume central limit theorem works in most scenarios. Again, that's kind of the caveat. Okay, let's take a look at like one more, and then we'll, I think we can call it a day. Or I don't know if you have a desire for a whole lot of these things. Okay. There's a lot of drugs and medicine examples in this textbook here. Okay, so this is like the other kind of classic scenario here for this particular kind of test. So we say an experiment was conducted to survey the effect of tamoxifen, I'm not sure, on patients with cervical cancer. One of the measurements made, both before and after tamoxifen was given, was microvessel density, MVD, which is measured as the number of vessels per millimeter square, as a measure that relates to the formation of blood vessels that feed a tumor and allow it to grow and spread. Okay, thus small values of MVD are better than large values, and here are the numbers that we have. Okay, and we have patient 1 through 18, and we have MVD before and MVD after. Okay, so what test would we apply here? Paired data t-test, right? And for that, we would need to calculate a difference column. And so this would be before minus after, and et cetera, et cetera, et cetera. Okay, so you have to do that for all of the patients. And then once you find the before versus after column, your null hypothesis is that the mean difference is 0, and the alternative is, I guess we're hoping that the mean difference is greater than 0. That is to say that the before minus after is greater than 0. That before we had large MVD, and after we want small MVD, right? Indicates that the drug is effective. Right. So you have to kind of read the problems carefully and see which direction is appropriate. Like, do we have a greater than or less than sign? And these things are hard. Okay, depending on how we've done this. Okay. Are there questions, requests? Yes.
So just to clarify, like when you open note, it's like I can bring a notebook.
Yes, you can bring your notebook. You can bring your textbook. We're going to say no phones, no iPads, no computers. Okay. So your notebook, I guess if you want to print some stuff out, that's fine. But nothing that connects to the internet or something like that. Okay. So we'll do that. I'll see you guys on Saturday. And we'll end there. Yeah. All right. Oh, wait, sorry.
Is it down here?